Look at Earth from orbit, and you will see a massive, churning ocean of gas, held tight against the surface by the planet's gravity. In any fluid, whether liquid or gas, the pressure you experience at a given depth is determined strictly by the physical weight of the material resting directly above you. But the atmosphere behaves very differently from the ocean. Water is an incompressible fluid. Its density stays almost exactly the same, whether you are measuring it at the surface or at the bottom of the Mariana Trench. Because oceanic density is constant, water pressure builds in a simple, predictable, linear progression as you dive deeper. Air, however, is highly compressible. Its density depends almost entirely on the amount of pressure actively crushing it. This creates a recursive physical loop. The air right at sea level is compressed by the entire weight of the atmosphere above it. That compression makes the bottom layer much denser and heavier, which in turn amplifies the compression on the air immediately beneath it. This recursive relationship guarantees that atmospheric pressure cannot decay in a steady, linear way as you move upward. Instead, the pressure drops off at a rapid, exponential rate the higher you climb. To map out this exact behavior, meteorologists rely on a specific reference framework called the U.S. Standard Atmosphere Model. This graph plots altitude against pressure. Displaying this as a straight line requires a trick on the horizontal axis. Notice the logarithmic scale. The physical distance between 10 and 100 hectopascals is drawn identically to the distance between 100 and 1000. If we plotted these exact same pressure values on a standard linear scale, that straight line would instantly collapse into a sharp, plunging exponential curve. Because basic linear intuition fails entirely as you leave the ground, we must rebuild our mathematical models of the atmosphere from absolute first principles. We start at the bedrock of classical physics, applying Newton's laws to a static fluid. Outside of extreme events like hurricanes or thunderstorm updrafts, the atmosphere has essentially zero vertical acceleration. It is locked in a mechanical stalemate. To understand this stalemate, we isolate a theoretical 3D air parcel. First is the downward pull of gravity against its mass, calculated as density times gravity times thickness. Pushing up is a differential pressure force from the denser air below. Because our theoretical air parcel is not accelerating up or down, these two opposing vectors must be perfectly equal. Translating that physical balance into mathematics gives us the hydrostatic equation. Change in pressure over height equals negative density times gravity. It is an elegant statement, but currently unsolvable. To calculate the pressure, we need the density. But as we established earlier, density is a moving target that changes whenever the pressure changes. To break this circular dependency, we have to eliminate the variable of density entirely by using the ideal gas law. The ideal gas law defines density as a function of pressure, temperature, and molecular mass. We substitute that relationship directly for the density symbol. Rearranging the algebra groups all pressure variables on the left and altitude on the right. But integrating this equation from sea level all the way to the top of the atmosphere requires one massive assumption. We invoke the isothermal assumption, temporarily pretending that the temperature of the entire atmosphere is perfectly constant from top to bottom. Fixing temperature in place allows us to complete the integration, resolving the calculus into the final barometric equation. The presence of Euler's number, the letter E, in the exponent mathematically proves the rapid exponential decay of pressure that we observed on the graph. And while this proof resolves the math, it introduces a strange new universal constant governing that decay, the letter H. The H stands for scale height. It is a metric representing the overall physical thickness of an atmosphere based on its specific temperature and gravity. Mathematically, scale height defines the specific vertical distance you must travel upward for atmospheric pressure to decrease by a factor of E, dropping to roughly 37% of its starting value. On Earth, assuming an average temperature, that 37% density mark sits at a scale height of approximately 8.5 kilometers. Temperature expands an atmosphere, pushing scale height up, while gravity compresses it down. Mars's lower gravity stretches its pressure gradient, resulting in 11.1 kilometer scale height. Venus features extreme heat and lower gravity, pushing its scale height to 15.9 kilometers. Scale height provides a clean metric for analyzing the architecture of any planet's atmosphere. Yet, this entire theoretical framework relies on the isothermal assumption, which is physically impossible. Earth's atmosphere does not maintain a constant temperature. This U.S. standard atmosphere chart shows the true temperature profile of Earth's atmosphere is highly erratic. In the troposphere, temperature drops sharply, but crossing into the stratosphere, ozone causes the temperature to reverse and heat up before plunging again in the mesosphere. Because temperature fluctuates so wildly depending on your altitude, applying a single mathematical integration across the whole atmosphere produces massive errors. Instead, meteorologists must divide the atmosphere into manageable chunks, calculating the pressure layer by layer using an entirely different tool, the hypsometric equation. This diagram shows a geometric air column. The hypsometric equation measures a cross-section's physical thickness using its average virtual temperature. By isolating the mass between the 1,000 and 500 hectopascal boundaries, we precisely calculate that distinct layer's thickness. Chopping the atmosphere into these discrete, averaged blocks is the only mathematically valid method for navigating a fluid where the temperature is always moving. To reach total precision, we have to break one final assumption, the idea that the acceleration of gravity remains a flat constant. According to Newton's law of universal gravitation, gravity weakens the further you move away from the Earth's center of mass. Measuring the atmosphere using raw geometric altitude, the straight distance on a Cape measure, causes critical calculation errors regarding the thermodynamic energy actually required to lift a mass of air vertically. The ultimate correction is geopotential height. It is an adjusted altitude metric that normalizes actual physical height against standard sea-level gravity. When you look at standard aircraft altimeters or severe weather prediction models, they are not displaying geometric distance. They operate strictly in geopotential height. High-speed aircraft traversing these pressure layers rely entirely on these normalized thermodynamic models to accurately gauge their environment and stay airborne. True mastery of atmospheric physics, whether you are predicting global weather patterns or designing spacecraft to reach orbit, requires abandoning perfect theoretical assumptions. You must continuously calculate for the dynamic, shifting realities of pressure, temperature, and gravity.